Welcome to the Deep Dive, where we take fascinating topics and, well, extract the knowledge you need to know.
Today, we're tackling a really big one.
Yeah, artificial general intelligence, AGI. You can think of it as the original moonshot, maybe, of AI research, creating machines that can think and learn as broadly, as effectively as humans.
Exactly. And, you're probably already encountering AI in your daily life, things like personalized recommendations, search engines.
Sure, all that stuff.
But that's usually what we call narrow AI, systems that are brilliant, but only at very specific tasks. AGI aims for something much, much wider, like human intellect.
Right. I remember reading, I think it was Ray Kurzweil, pointed out that narrow AI is great inside its box, but change the rules just a tiny bit. And, well, it often needs us humans to jump in, right? To reprogram it.
That's it. Your navigation app, fantastic for finding the fastest route. But you wouldn't ask it for dating advice. Or probably shouldn't anyway.
Probably not. So that's the key difference then.
That really is the core distinction, yeah. AGI is all about that human-like ability to generalize, to take what it learns in one area and apply it somewhere completely new.
Like learning different skills, adapting on the fly.
Exactly. It's what researchers often call transfer learning, something, we humans do pretty effortlessly most of the time.
So we're talking more like the sci-fi AI, the ones that feel genuinely intelligent, R2-D2 figuring things out.
Yeah. Or maybe a chatbot that could actually discuss anything and, understand you, not just pattern matching.
That flexibility, handling the unexpected, that's AGI.
That's the hallmark, precisely. And our mission today in this deep dive is really to unpack this huge, ambitious goal.
Okay.
We'll explore the main ways researchers are trying to actually build AGI, looking at the detailed information we've got here.
Great. So what's the roadmap?
Well, to give you a quick overview, we'll be looking at 4 main categories of approaches. There are symbolic approaches, trying to build intelligence using symbols, then emergentist approaches, which hope intelligence will sort of arise from more basic stuff.
Right.
Then hybrid approaches, trying to combine those two. And finally, a more theoretical angle, the universalist perspective.
Got it. 4 main ways. Where should we start? Maybe the symbolists.
Let's dive in there. The symbolic approach, it operates on something called the physical symbol system hypothesis.
Okay, what's that mean in plain English?
The core idea, basically, is that intelligence comes from manipulating symbols. Think words, concepts, things that represent the world, or even the AI itself. These systems usually have a central control unit, and they focus on managing information in a sort of mental workspace, a working memory.
Okay, so it's not just crunching numbers like a calculator. It's working with symbols that have meaning, reasoning through ideas.
Pretty much, yeah. But what are some of the, the big challenges with thinking about intelligence this way?
Yeah, where does it struggle?
Well, symbolic systems can be really powerful for certain kinds of logic, like deductive reasoning.
Okay.
But historically, they've had a tougher time with things that feel more natural to us, like learning from messy real-world data or being genuinely creative.
Right.
And also remembering specific experiences like episodic memory or even just learning new procedures through practice.
But it's not a dead end, right? The source mentions some successes too.
Oh, absolutely. There's been progress, techniques like genetic programming, GP, inductive logic programming, ILP, and Markov logic networks, MLNs.
Okay.
These have shown they can actually learn symbolic relationships and even handle quantitative data, numbers.
Interesting.
What's kind of interesting, though, is how they learn. Sometimes it feels a bit like the intelligence is sort of emerging from the symbol interactions, almost blurring the lines with those bottom-up approaches we'll talk about later. And sometimes, honestly, it's not totally transparent why they reach a certain conclusion. A bit of a black box sometimes.
Fascinating. So they can learn and reason, but maybe not always in a way we fully understand. Can you give us some concrete examples, actual systems?
Sure. ACTR is a big one. It's mostly symbolic, but it does have a bit of a connectionist flavor.
How so?
Think of it like ideas activating related ideas, almost like spreading activation in the brain, but not a full neural network. It's been really useful for simulating how humans do various cognitive tasks.
Okay. And then there's psych. Heard about that one, this massive effort to write down all of human common sense.
That's the one.
Yeah.
Psych uses what's called predicate logic. Think of it like expressing knowledge in logical statements. All cats are mammals. Paris is the capital of France, that kind of thing. And it has this absolutely enormous database of these statements. The idea being, if you give it enough basic common sense knowledge, it can reason like a human.
Wow.
People have looked at using it for natural language understanding, even controlling robots, connecting it to other systems like Albus's 4D RCS. The core idea was that just having this huge base of explicit knowledge might be the key.
But that sounds incredibly ambitious, just manually encoding all that.
Exactly. The scale, the difficulty of capturing common sense explicitly, that turned out to be a massive hurdle.
Makes sense. What are some other symbolic systems?
Well, there's EPIC. It models how humans perceive, think, and act using production rules controlling parallel processors.
Okay.
Icarus is designed more for physical agents, like robots, giving them reactive skills to solve problems based on their goals.
Right.
SNEPS has been around for decades, actually. It uses logic, frames, and networks for things like language processing and building virtual agents.
A long history there.
And SO, that's a classic rule-based system modeling general intelligence. It's been extended recently to handle more sensory and motor stuff, and even reinforcement learning.
So, boiling it down, what's the main argument for the symbolic approach and the main argument against it?
The core argument for is that this kind of symbolic reasoning, abstract thought, that's what really defines human intelligence and lets us generalize so powerfully. Proponents believe we can capture that logic in AI, maybe even independent of the messy biological details of the brain.
And the against.
Critics argue these systems often lack the kind of flexible, emergent behavior we see in nature, that they feel brittle. And maybe they're too disconnected from, sensing and acting in the real world to ever truly get to human-level smarts.
That tees things up perfectly for our next category.
Yeah.
The emergentist approaches. Sounds like a totally different philosophy.
It really is a shift. The emergentist view is basically that intelligence, even the high-level stuff like reasoning, will sort of bubble up. It'll spontaneously arise from the interactions of lots of simpler, lower-level components.
Subsymbolic dynamics, the source calls it.
Exactly. Think of how a flock of birds creates these complex patterns from simple rules each bird follows, that kind of idea. And they often draw inspiration from neural networks, from how our brains are wired.
And what are the strengths of going bottom-up like this?
Well, these emergentist systems tend to be really good at finding patterns in huge amounts of complex, messy data. Think image recognition, speech understanding.
Right, deep learning territory.
Yeah, and also reinforcement learning by trial and error and making associations, linking different bits of information together. Associative memory.
But where do they currently, fall short compared to us?
Despite making incredible strides, especially with deep learning.
Yeah.
Purely emergentist approaches haven't yet, arguably, shown a really convincing ability for complex, abstract reasoning, or for truly understanding and generating nuanced human language, though lots of research is pushing in that direction.
Okay, so let's look at some specific examples again. Emergentist architectures.
Sure. Destin is one. It's a system that learns patterns hierarchically over time. It actually got integrated into that cog prime architecture we might touch on later.
Ah, interesting.
Hierarchical temporal memory, HTM, is another, Jeff Hawkins' work. Modeled specifically on the structure of the cortex, it's been used mainly for vision tasks so far. SEL, the spatially aware learning architecture, aims to simulate how different brain areas work together. It's been used in psychological and language simulations.
And you mentioned neural Darwinism earlier.
Yes, systems like Nomad and its successors, they're based on Gerald Edelman's ideas, using simulated neurons that sort of evolve or get selected over time to handle sensor-motor tasks, categorization.
Right.
Ben Kuiper's work is also really interesting here. He combines qualitative reasoning, thinking about qualities, not just numbers, with reinforcement learning. The goal is for robots to learn world models autonomously. He calls it bootstrap learning.
Bootstrap learning, yeah.
And Svea Ackler has developed neural networks where the connections, the weights, adapt in a way that seems to give them symbolic-like meaning, potentially bridging that symbol-sub-symbol gap.
So many different angles.
Yeah.
And the source also mentioned deep learning's impact more broadly.
Absolutely. I mean, researchers like Andrew Dang, Tommaso Poggio, Jan LeCun, Jeffrey Hinton, They might not always frame their work as building full cognitive architectures,
Right.
but the breakthroughs in deep learning are massively relevant. Building these layered neural networks that learn features automatically from data, often inspired by visual processing in the brain, it's led to huge advances. Image recognition, speech.
Yeah, absolutely everywhere now. So the big for and against for emergentism as the path to AGI.
The big four is, well, our own brain. It's the prime example of intelligence emerging from a self-organizing network. Proponents really emphasize the potential for flexibility, adaptability.
Learning from experience.
Exactly. The main against argument is that maybe just focusing on the hardware, the biological inspiration, isn't enough. Are we missing the crucial high-level organizational principles, the software of intelligence? And some critics wonder if these approaches, by their nature, might struggle to achieve the kind of abstract symbolic reasoning that seems so central to human thought.
That leads us really nicely into the next area, computational neuroscience. Trying to build AGI by directly modeling the brain.
Yeah, the logic here is pretty straightforward. If we can simulate the brain accurately enough, maybe we can replicate its intelligence.
Seems logical, but easy.
Definitely not easy. The brain is unbelievably complex, and frankly, we still don't fully understand how it works. Simulating it is a monumental challenge.
The source lists some seriously ambitious projects here. Can you give us a sense of the scale and maybe the different goals?
Sure. You have things like Henry Markram's Blue Brain Project, which evolved into the Human Brain Project. Their goal is incredibly detailed simulation, modeling individual ion channels in neurons, aiming eventually for the whole human cortex.
Wow, that's granular.
Then there's Dharmendra Moda's Cognitive Computation Project at IBM. They took more of a reverse engineering approach, simulating synaptic connections, and achieved a scale roughly equivalent to a cat's cortex a while back.
Cat's cortex. Still impressive.
And Kwabena Bohan's NeuroGrid project is different again. They focus on building custom computer chips, neuromorphic hardware that directly mimic how neurons compute. Things like silicon retinas, self-organizing chips.
So specialized hardware, not just software simulation.
Exactly. That's neuromorphic engineering.
What other big projects are out there?
Barry Horowitz at the NIH simulates dynamic neural networks to understand cognitive tasks like hearing or language, using actual brain imaging data like fMRI to guide the models.
Using real brain data.
Okay. Eugene Isikovich and Gerald Edelman developed a very large-scale model of the thalamocortical system, the interplay between the thalamus and cortex. It could reproduce certain key that formed the basis for Isikovich's company, the Brain Corporation.
Right.
And then there's Marcel Just's 4CKPS. That one's interesting because it explicitly tries to bridge computational neuroscience and symbolic AI. It aims to explain both human behavior and the patterns seen in brain imaging data.
So quite a mix of goals, biological accuracy, functional similarity, new hardware.
Exactly. It's not all just one thing. And a key takeaway seems to be that right now, the biggest bottleneck might not actually be raw computing power, surprisingly.
Oh, what is it then?
It's more our lack of complete knowledge about the brain itself. There's still so much we don't know about the wiring, the algorithms the brain uses. The neuroscience side needs to catch up, in a way.
Got it. So the pros and cons of trying to build AGI by simulating the brain.
Well, the strongest argument for it is pretty simple. The brain is the only example we have of general intelligence. So copying it seems like a reasonable strategy, right?
Makes sense.
And as neuroscience advances and our simulation capabilities grow, this path could become really powerful.
But the downsides?
Critics point out, first, our incomplete brain knowledge. We're trying to copy something we don't fully understand. And second is directly replicating biology on digital computers, which work fundamentally differently, the most efficient way. Maybe designing AI algorithms from first principles is better.
Okay, that covers neuroscience. Next up is a different kind of biological inspiration. Artificial life or a life. Not modeling the brain, but simulating evolution itself.
Exactly. The core idea here is, let's create artificial ecosystems, virtual worlds with simple artificial organisms. Let them interact, compete, reproduce, evolve over generations. And the hope is that, just like intelligence evolved in nature, maybe general intelligence could emerge spontaneously from this complex evolutionary process in simulation.
That sounds incredibly long-term and computationally heavy. How's it going?
Well, artificial life is a fascinating field, but yeah, the organisms created so far are still extremely simple compared to, say, an insect, let alone something generally intelligent.
Right.
A huge challenge is achieving what's called open-ended evolution, where genuine novelty and increasing complexity arise continuously without being pre-programmed. It's hard to get that kind of creative explosion going.
Are there specific projects trying this?
The source mentions Bruce Dahmer's EvaGrid project. It tries to tackle some limitations by using detailed chemistry simulations within the artificial life framework running on distributed computing, but it's still early days.
And the main hurdle is still.
Computational resources, mostly. Simulating entire ecosystems with enough detail and for enough generations to potentially see intelligence evolve, that takes immense computing power. But, as computers get faster, maybe this approach becomes more feasible down the line.
Interesting long shot. Okay, our final emergentist-related area is developmental robotics. This sounds more grounded robots learning like babies.
Pretty much. The focus here is on building robots that learn about the world through their own actions and sensory experiences, starting with minimal pre-programmed knowledge, like a child exploring its environment. A key concept here is intrinsic motivation. Instead of just programming goals, you build robots that are driven by things like curiosity, a desire to explore novelty, to understand things they don't understand yet.
And this isn't a totally new idea. The source mentions Schmidhuber again.
Right. Jürgen Schmidhuber did a lot of foundational work here decades ago, emphasizing how a robot's own sense of learning progress or curiosity could drive it to explore and learn complex skills without external rewards.
And now we're seeing more advanced robots applying these ideas.
Exactly. With better robots, better sensors, more computing power, these developmental principles are being tested more seriously.
Can you give us some examples?
Sure. Jianweng's DAV and SAIL projects involved mobile robots that learn tasks by building their own internal world models directly from their sensorimotor data stream, very much inspired by child development.
Okay.
Then there's the Flowers Project, led by Pierre Evadier and Frederick Kaplan. They explicitly aim to model how a child's mind develops, driven by this intrinsic motivation. They have things like the Robot Playroom, where robots experiment freely, and research on how language can be learned through interaction.
A robot playroom. Cool.
And the I'm Clever project, involving Gianluca Baldassar, focuses specifically on the iCov robot, that humanoid robot, enabling it to explore and learn childlike behaviors driven by these internal motivational signals.
So what's the case for and against developmental robotics for AGI?
Supporters argue, look, the way babies and young children learn unsupervised exploration, interacting with the world, that's the only proven example we have of going from essentially zero knowledge to broad intelligence. We should try to replicate that process.
Makes intuitive sense.
Critics, though, point out that current robots are still, frankly, quite crude compared to the human body and sensory system. There's a worry that focusing too much on the specific challenges of robotics, getting a robot to walk, grasp things, might distract from the core cognitive challenges of AGI.
Right, getting bogged down in the physical details.
Yeah, and there's also a more fundamental question. Is all that detailed sensor and motor grounding, that physical interaction, actually necessary for high-level reasoning in AGI, or could you achieve it more abstractly? That's still debated.
Okay, so we've covered symbolic, emergentist, neuroscience, A-life, developmental robotics. Now, what about hybrid AGI architectures, trying to combine things?
Exactly. This seems like a very natural step, right? If symbolic systems are good at reasoning and emergentist systems are good at pattern recognition and learning from data, why not try to get the best of both worlds?
Makes sense.
So many researchers are exploring ways to integrate these different approaches. It could be having separate symbolic and neural components that talk to each other, or maybe even systems where symbols themselves emerge from an underlying neural layer.
The source quotes Nielsen on grounding symbols. What was his point?
Nielsen argued that, symbolic reasoning is crucial for higher-level thought. But those symbols need to mean something in the real world. They need to be grounded in perception and action. He believed true human-level AI would require both symbolic and non-symbolic processing working together.
Integrated. And the goal is often described as cognitive synergy.
Right. Cognitive synergy. The idea that the whole system, by combining different mechanisms, becomes more capable than just the sum of its individual parts. You get emergent capabilities from the interaction.
Okay, let's look at some examples. How are people actually building these hybrid systems?
Well, Clarion is one prominent example. It explicitly combines symbolic reasoning, using what it calls explicit knowledge, with Connectionist, neural network-like processing for implicit knowledge. Though in Clarion, the learning mechanisms for these two parts are somewhat separate.
Okay, distinct layers.
Cog Prime, which, full disclosure, is a project I've been closely involved with, takes a different tack. It aims for deeper integration, using multiple learning algorithms in different memory types, symbolic, attentional, procedural, all operating on a shared knowledge representation, a kind of graph structure. The goal is that cognitive synergy. We're exploring it in video game agents, planning towards robotics.
Deeper integration.
Yeah.
Okay. What are some other hybrid approaches?
DUAL is interesting. It's inspired by Marvin Minsky's Society of Mind idea.
Right, lots of little agents working together.
Yeah. In DUAL, these agents have both symbolic and connectionist aspects, and they self-organize to handle tasks like perception or making analogies. LIDA is another one. It's a very broad architecture based on Bernard Barr's global workspace theory, the idea of a central information clearinghouse in the mind. LIDA integrates many different memory systems and processing modules within a cognitive cycle, though its current focus seems to be more on, let's say, lower-level intelligence aspects.
Got it. Foundational stuff.
MicroPsy is based on Dietrich Derner's psi theory, which emphasizes motivation and emotion as core parts of intelligence. It's been tested in control applications, virtual worlds. Again, maybe focusing more on the foundational, motivational side currently.
So a real variety in how these systems are put together.
Oh, definitely. Polyscheme integrates multiple different reasoning methods, like different specialists for general problem solving. It's even been used to model how infants reason. Yeah. Shruti is a biologically inspired connectionist model for handling relations and rules. And Albus's 4D RCS, often used in robotics, has a hierarchical structure like some emergentist systems, but relies more on hardwired architecture, intended to be augmented by learning.
So some are more modular, like plugging components together. Others aim for really tight integration.
Exactly. That's a key distinction. The tighter integration might offer more potential for synergy, but it's also much harder to design and understand.
So the arguments for and against hybrids.
The main argument for is, again, looking at the brain. It seems incredibly complex. A hybrid system using diverse mechanisms. So maybe combining approaches in AI is the best way to mirror that functionality.
Makes sense.
The against argument. Well, critics worry you might just be gluing together two inadequate systems and not actually solving the core problems. There's also concern about complexity. These systems can become very intricate, maybe brittle, hard to debug. Violating Occam's razor, perhaps keep it simple.
Right. Okay, one more major approach to cover. The universalist approach. This sounds very different, more mathematical.
It is, yeah. It's much more theoretical. The universalist approach basically starts by asking, what would the mathematically optimal, generally intelligent algorithm look like if we had, like, infinite computing power?
Wow, okay. Not very practical starting point.
Not immediately practical, no. But the idea is, if you can define that theoretical ideal, maybe you can then figure out how to approximate it with realistic resources.
Where did this line of thinking start?
The roots go back to Ray Solomonoff's work on the theory of induction, how to make optimal predictions from data.
Okay.
The prime example today is Marcus Hutter's AIXI system. It's described as a meta-algorithm. In theory, it searches through the space of all possible computer programs to find the one that maximizes its future rewards in any computable environment.
Searches all possible programs.
In theory, yes. And mathematically, under certain assumptions, AIXI is provably the most generally intelligent agent possible. But it requires literally infinite computation.
Right, kind of limiting.
There's a slightly more constrained version, AIXIO, but even that needs way, way more computing power than anything imaginable.
So it's a beautiful theory, but not something we can build.
Not directly, no. But it inspires a research program, scaling down from infinity. Can we find practical algorithms that capture some of AIXI's theoretical power, but work with feasible resources?
Any other examples of this thinking?
Jürgen Schmidhuber's Gödel machine is a related concept. It's an AI that could theoretically prove that its next action is the optimal one for achieving its goals, based on its current knowledge and axioms. Again, in its pure form, it's uncomputable.
Okay, so are there any practical results from this scaling down?
Researchers like Joel Van Ness have shown some promising results applying simplified versions of these universalist ideas to specific problems, like reinforcement learning in certain contexts.
But getting from that to human-level AGI with realistic computers, That's the big question mark.
That's the huge leap, exactly. It's a very abstract approach, divorced from the biological specifics of human intelligence or the messiness of real-world interaction.
So the arguments for and against the universalist path.
Supporters see it as providing a rigorous mathematical foundation, like theoretical physics providing idealized models. By defining the ultimate target, maybe we gain insights for practical designs. It forces clarity about what general intelligence even means.
Yeah, mathematical rigor. Okay.
Critics argue that intelligence in a theoretical infinite resource world might have very little relevance to achieving it in our finite, messy reality. They think intelligence is deeply tied to embodiment, interaction, resource limits, things these models abstract away.
It might be missing the point of real-world smarts.
That's the concern, yeah.
Okay, so we've surveyed these different grand approaches. And the source shifts gears a bit, focusing specifically on AGI that could function like a human. And it introduces this integrative diagram.
Yes. This diagram isn't presented as the answer, but more as a synthesis. It pulls together ideas from many of the approaches we've just discussed. It's a set of 7 figures trying to sketch out the key components and processes we think might be necessary for an AI to achieve human-like general intelligence. Think of it as a visual overview of the current rough consensus, or at least a plausible picture.
The kind of requirement sketch. Not a blueprint, but a map of the territory.
That's a good way to put it. It's didactic, meant to help organize thinking.
So can you give us a quick tour? What are some of the key parts shown in these figures?
Okay, figure 1 gives a very high-level structure, adapted from Aaron Sloman's work, actually. It shows things like working memory, long-term memory, reactive processes that respond quickly, deliberative processes for slower thinking, language, and reinforcement learning. It notably adds more emphasis on language and reinforcement compared to Sloman's original.
Okay, the big boxes.
Figure 2 then zooms into working memory and reactive processing. This one is modeled pretty closely on the LiDAR architecture. It shows sensory input coming in, motor output going out, maybe handled by deep learning components, an action selection mechanism, maybe like the Psi model we mentioned, deciding what to do next, and its interaction with a multi-part long-term memory.
Got it. What about things like motivation? Memory.
Figure 3 focuses specifically on motivation and action selection, drawing heavily from that Psi model, but embedding it within the larger cognitive picture and adding a reinforcement component. It overlaps with Figure 2, but gives more detail on choosing actions, planning.
Okay.
Figure 4 dives into long-term memory and higher-level thinking deliberation, metacognition, thinking about your own thinking. This draws more from my work on cognitive synergy, distinguishing different types of long-term memory, declarative facts, procedural skills, episodic experiences, sensory motor patterns, attentional focus, even goals, intentional memory, and crucially, how these different memory systems might interact synergistically. It also includes metacognition, suggesting it uses similar processes to regular thinking, just applied to the system's own internal states.
So different kinds of memory working together. What about perception and action?
Figure 5 tackles multimodal perception, drawing a lot from deep learning ideas. It shows hierarchical processing for senses like vision and hearing, with information flowing both bottom-up from the senses and top-down from expectations or context. It also notes cross-connections between senses and acknowledges simpler senses like touch and smell. Figure 6 then looks at action and reinforcement. It proposes hierarchical action subsystems, different levels of control for different body parts, linked together and connected back to perception. It includes motor planning and also a hierarchy for processing reinforcement signals, referencing Albus's work here.
And language gets its own focus, too.
Yes. Figure 7 treats language as tightly coupled perception, understanding speech text, and action, generating speech text. It shows a hierarchical structure from sound swords up to meaning for comprehension, and the reverse flow, from ideas down to sentences for generation, with feedback loops involved.
It's quite comprehensive. But what about something like creativity? Is that in there?
That's a good question. The source suggests that creativity isn't seen as a separate box or module in this kind of view. Instead, it's considered more likely to be an emergent phenomenon, something that arises from the complex interplay of all these other components. Memory, reasoning, perception, motivation.
I see. So this whole diagram is like a target spec for human-level AGI, highlighting the parts and interactions we need to figure out.
Exactly. It lays out the kind of functional capabilities and interconnections that a human-like AGI would likely need to possess based on our current understanding.
Which brings us to a crucial point. How do we actually measure progress towards this incredibly ambitious goal? How do we know if we're getting closer?
Yeah, measurement is critical in any science, and AGI is no exception. Progress depends on knowing if you're making progress.
Right.
Now, focusing specifically on human-level AGI actually simplifies the measurement problem somewhat, compared to measuring general intelligence in the abstract.
How so?
Because we can potentially use tests designed for humans. Measuring intelligence beyond human level gets very abstract, relying more on mathematical definitions. But for human level, we have benchmarks we can try to meet.
Okay. And the source links metrics to the environment the AI operates in.
Yes, that's a key point. How you measure intelligence depends heavily on where the AI is acting. Is it just text chat? Is it navigating a virtual world? Is it controlling a physical robot?
Right. Different challenges, different ways to test.
So the field is moving towards this idea of scenarios, a specific environment, plus a set of tasks to perform in it, plus the metrics used to evaluate success. Shared scenarios would be great for comparing different AGI systems, but getting everyone to agree on standard ones is still a work in progress.
Okay, so let's talk about quantifying that big milestone, actually reaching human-level AGI. What specific tests or benchmarks have been proposed?
Well, there are quite a few ideas floating around. The classic Turing test, of course. Can an AI fool a human judge in conversation?
The old classic. Still relevant.
It has its weaknesses, maybe focuses too much on imitation, deception, but it's a start. A more modern take is the virtual world Turing test. Can an AI control an avatar in, say, an online game world and be indistinguishable from human players?
More embodied.
Yeah. Then you have more formal mathematical measures. Shane Legg proposed the AIQ measure based on information theory, trying to quantify intelligence across diverse tasks. Hernandez-Araujo and Dow have similar concepts. The Hutter Prize for text compression is another angle, based on the idea that prediction is key to intelligence.
Text compression, how does that relate?
The better you can compress data, the better you understand its underlying patterns, which is related to prediction and learning. It's a very specific, objective measure.
Interesting. What else?
Then there are more real-world competency tests, like the online university student test. Could an AGI enroll, take courses, and get a degree entirely online?
Wow.
Or even harder, the robot university student test, doing the same at a physical university, attending classes, labs.
It requires embodiment, too.
Definitely. And maybe the ultimate test, sometimes called the artificial scientist test, or even the Nobel Prize test. Could an AI conduct high-quality, original scientific research and make significant discoveries?
That's setting the bar high. So each of these has pros and cons as the definitive test.
Pretty much. Some might be passed by clever, narrow AI. Some might not capture the full breadth of intelligence. Some might be too difficult initially. But the source suggests that, taken together, they give us a reasonably good handle on what we mean by achieving human-level general intelligence. They make the goal more concrete.
Okay, that's the ultimate goal. But what about measuring the incremental progress? Getting, say, halfway there. That sounds much trickier.
It really is a major challenge. How do you quantify being, 50% as generally intelligent as a human? It's not obvious.
So what do researchers do now?
Well, the source notes that based on discussions with AGI researchers, there are lots of practical tests people use internally or propose, things that seem like they should require general intelligence.
Like what?
Examples mentioned from an AGI roadmap workshop include the Wozniak coffee test. Steve Wozniak suggested a truly intelligent robot should be able to walk into an arbitrary house and figure out how to make coffee.
I like that one. Practical.
Others include story understanding, really comprehending narratives, passing elementary school reading curricula, learning to play arbitrary video games just from the screen input, or even passing evaluations designed by child psychologists for different developmental stages.
Interesting range. But the worry is?
The worry for many is that these specific tests, while challenging, might still be gameable. That a sufficiently sophisticated narrow AI, maybe trained specifically for that test, could pass it without possessing true, flexible general intelligence. There's disagreement on whether these tests capture the core of AGI or are just difficult AI problems.
A fundamental debate, then. Yeah. Are there other ways people try to measure progress?
Yeah, the source mentions more computer science-oriented ideas, too, like multitask learning. How well does an AI learn and perform across a wide range of different tasks? Or shaping presenting the AI with progressively more difficult versions of a task. Or Zvi Akler's idea of flexibility of recognition. How well does a system adapt its learned concepts when the input changes or context shifts?
These sound more abstract.
They are. And while valuable, the question remains, Do these abstract measures, often tested on standard AI benchmark problems, really capture the richness and subtlety of real-world human intelligence and tasks?
Right, like the general game player competition AI learns to play any game given the rules. That needs generality.
It does require significant generality, yes. But does mastering abstract board games or logic puzzles necessarily translate to the kind of intelligence needed to navigate the physical and social world? It's not clear.
And there's a deeper question about the real world itself.
Yeah, are the specific statistical patterns and structures found in human environments and tasks universally relevant for any AGI? Or are they just quirks specific to building human-like intelligence? We lack a solid theory to tell us right now.
This all circles back to, why is measuring incremental AGI progress so darn hard? Is it just that we need better tests? Or is there a more fundamental problem?
The source raises a really interesting possibility: the cognitive synergy hypothesis.
We mentioned synergy before with hybrid systems. How does it apply here?
The idea is that maybe AGI isn't something you get gradually. Maybe you need a certain critical set, a critical mass of different key cognitive components: memory, reasoning, perception, learning, etc., all working together effectively. And if you're missing even one or two crucial pieces, the system's overall general intelligence might be drastically lower. Not just a bit worse, but fundamentally handicapped.
So it's not a smooth ramp up, but maybe more like a step change once you have all the core pieces.
Potentially, yes. And it gets worse with the tricky cognitive synergy hypothesis.
Tricky synergy.
This suggests that not only do you need all the parts working together, but building components designed for this kind of synergistic integration might be inherently much harder, much more complex than building standalone components for simpler, narrower AI tasks.
Okay, and how would that make measuring progress difficult?
Well, tricky synergy holds a partially built AGI system, even if it has some really sophisticated components designed for eventual synergy, might perform worse on specific benchmark tests than a simpler, narrow AI that was optimized just for that single test.
Ah, I see. The incomplete AGI looks dumber on the test, even though it might be closer to the real goal overall.
Exactly. It would make tracking genuine progress towards integrated AGI very difficult, using tests that narrow AI can easily ace. We don't know for sure how big a factor tricky synergy is, but it highlights a potential deep reason why measuring incremental progress is so problematic.
Which really underscores the need for a better theoretical understanding. What would a good general theory of general intelligence actually look like? What should it be able to do for us?
Yeah, the source acknowledges that AGI theory right now is kind of a patchwork compared to mature scientific theories. But it lays out a wish list. What would a comprehensive theory ideally provide?
Okay, like what?
Ideally, it should help us determine the optimal AI architecture given specific goals, environments, and available resources.
That would be handy.
It should predict for which kinds of goals and environments a given architecture will be intelligent. It might even shed light on the likely subjective experiences, the qualia, of different AI systems.
Objective experience.
Wow.
It should help us synthesize appropriate tests for general intelligence. Help us identify concepts hidden inside non-symbolic systems like neural nets. Predict an AI's developmental path, estimate the likelihood it will follow certain behavioral rules, and how to build systems that balance intelligence with safety constraints.
Safety is crucial.
Absolutely. Identify the key structures needed for human-like AGI with feasible resources. Predict the societal consequences of deploying AGI, and even determine how to assess the ethical character of an AI.
That is an incredibly ambitious list for a theory. We're clearly not there yet.
Not even close. As the source says, right now, designing AGI systems often feels more like art or maybe craft than science. It relies heavily on intuition, tinkering, trial, and error.
Right.
A mature theory would make the whole process much more systematic, predictable, scientific. How we get such a theory, maybe a breakthrough by some genius, or maybe it emerges gradually alongside experimental progress. We don't know.
So wrapping things up now, let's revisit that core AGI hypothesis, the idea that general intelligence is fundamentally different, qualitatively different from narrow AI. Based on everything we've discussed, where do things stand? Is the hypothesis looking likely?
Well, the source offers a measured take, based purely on the scientific and engineering results achieved so far. The jury is still out. Yeah. On one hand, narrow AI hasn't spontaneously leaped into general intelligence despite huge progress. On the other hand, AGI-focused research hasn't yet produced systems with dramatically broad intelligence either. The theoretical arguments for the distinction are there, but they lack rigorous, large-scale empirical validation.
So we can't definitively say yes or no based on current evidence alone.
Not definitively, according to this analysis.
So what are the key things needed to really move the field forward and maybe get a clearer answer?
The source highlights two critical developments needed.
Okay.
First, the emergence of a broadly accepted, powerful theory of general intelligence. One that really characterizes it and tells us how to build effective architectures.
A solid theory.
Second, the practical demonstration of an AGI system that shows a dramatic and undeniable amount of general intelligence. Something unambiguous, like that preschooler robot learning autonomously, or a chatbot capable of truly coherent, insightful, long-form conversation across domains.
Practical proof of concept.
Exactly. Now, neither of those would be absolute mathematical proof of the core AGI hypothesis, but they would build immense confidence. The theory would likely imply it, and the demonstration would make it hard to deny.
It certainly feels like we're still in the early innings of this whole endeavor. It's such a huge challenge.
It is. But the source also ends on a note of, well, potential. Given the exponential pace of technological advance, particularly in computing and AI, progress could potentially accelerate rapidly.
Right. People make predictions.
Yeah, the source mentions surveys of AGI researchers, like one from AGI 2010, where many expressed optimism, predicting human-level AGI as likely sometime before 2050, with some even more optimistic. Of course, predictions are hard, especially about the future.
As they say.
But the level of dedication, the ingenuity being applied by researchers across all these different approaches, it suggests we're definitely on a fascinating journey.
A fascinating journey indeed. And maybe on that note, we can leave you, the listener, with a final thought to mull over. Considering the truly profound implications of creating artificial general intelligence, which of these diverse approaches we've talked about today strikes you as the most promising path forward? Why does one resonate more than others? It's definitely something worth thinking more about.
Absolutely.
Thanks for joining us for this deep dive.